Are we ready for example time? You knew that it was coming because we just introduced the addition of water and acid to our alkynes in the previous video. So let's do an example just so that you know what type of products are going to be formed from these reactions. So I'm first going to take CH3. Oh, I got a glitch already and we're not even a handful of seconds into the video. So I'm going to take CH3 and then carbon and triple bond and carbon and CH3. And we're going to add water and acid. Now, I'm just going to write H+, but keep in mind that they can also write an actual acid here. So, for instance, it's not uncommon to see something like H2SO4. We saw that in alkenes. We're going to see it in alkynes. There's no difference here. So, as usual, what is the process? What is the procedure? Let's learn about the alkenes. I took our reagent, CH3, carbon, triple bond, carbon, CH3, and I'm going to add water with the presence of acid to this molecule. Okay, so what we did before is that we erased a bond and we added 2 sites of attachment, didn't we? There we go. Well, what do we add on? H, OH. So think of this water as HOH, and there's our split. So hydrogen plays with other hydrogens. Well, it looks at these 2 carbons and it says, I don't really care where I go. I'm impartial. One carbon, it doesn't have any. The other carbon, it doesn't have any. So I don't really care where you put me. So we'll go to the left-hand side. And then that means the OH, the remaining piece, has to go on the other side. All right, so I'm just going to rewrite this as CH, and I'm going to take this hydrogen, and I'm going to erase it, and I'm going to erase that bond. All right, so just to clean it up, there we go. Well, you probably want to do this again, don't you? Stop. That's not what we do here with the addition of water and acid, because let's look at what we just formed. Look at this piece here. This is a carbon, double bond carbon with an OH. Folks, this is the enol that has formed. So, with the presence of the enol, we know that this is not very stable. We know that this molecule will prefer to rearrange to increase the stability before it goes forward. All right, so what does it do? Well, I'm going to erase this now that we realize that is the enol structure and that we do not end up with that structure. That is not our final answer. What we do is we erase this double bond between there. That double bond will now be drawn between the carbon and the oxygen. This hydrogen will be erased, and that hydrogen will go on to this spot. We do a switcheroo, just like we talked about in the last video. So this is the final product right here. This is the final product from this reaction, because at this point we have no double bond to react with again. It really self-deconstructs. It will go through a period of rearrangement and it will get rid of that double bond on its own. You do not need 2 moles of water in order for this process to go forward. So, can we identify this? The answer is yeah, we can. If we want to review, this C double bond O, this is called a carbonyl. So that carbonyl has formed. What type of carbonyl do we have? Do we have the aldehyde version or do we have the ketone version? And the answer is the ketone, because off of this carbon, I see a carbon to the left and I see a carbon to the right. So because it's flanked by 2 carbons, hydrogen's not one of them, right? There's 2 carbons, one on each end. This is a ketone. So we have formed a ketone. We do not know how to name the ketone, which is okay. Again, that comes later, but this is the product that we formed from this organic. Folks, that's all that you have to do with the water and the acids. It's slightly different. We don't really talk about excesses, and the reason is because we don't need it. Water and acid will go in and form the enol, and the enol will take care of itself and will rearrange on itself and it destroys that double bond on its own. We do not have to do that. All right. Now, it just so happens that this was a symmetrical molecule, which is good. This is not a problem. But sometimes we do not have a symmetrical molecule. All right, so what you see on this image slide is really the same thing that we've done. This up here at the top is a symmetrical alkyne. So this hydrogen will go onto either carbon and we end up with the same product. Again, if you don't believe me, draw the choices down and then look at where that C double bond O is going to be located. So the triple bond gets destroyed to a double and two sites of attachment open up. Hydrogen goes on one side, OH goes onto the other. It will rearrange. This will end up with a single bond. This will end up with a C double bond O. This is the third carbon in. And folks, look over here to this product. It's the third carbon in as well. So this gives you the same product no matter how you look at it because it's a symmetrical alkyne. It's the same on the first half as it is on the back half. Down here at the bottom, though, you do get a mixture. So this is an unsymmetrical alkyne. This triple bond is not located in the dead center of the molecule. So the left-hand side is different than the right-hand side. But if you look at these carbons, hydrogen still has no preference. Hydrogen that sometimes could go to the left and sometimes it could go to the right. And either one of these could happen. There's no rhyme or reason. Because it's unsymmetrical, because there is a choice, we do get different products in this version. And that's why you see them draw both. So triple bond breaks to a double, a side of attachment here and a side of attachment there. The OH could form here, it rearranges, and that is where the double bond is going to go. So in one choice, you will see the carbon double bond O onto the second version. That's what you see here, the second carbon. Well, I didn't have to do that, did I? Nope, I didn't have to do that. I could also destroy this triple bond to a double. Two sides of attachment open up, and the OH will go here. That will rearrange into a C double bond O. That is on the third carbon from the left, and that's what you see here. So both choices exist, and I write down both choices as well. All right, now let's do an example problem. Here we go. What ketones are formed from the acid catalyzed hydration of 3-heptine? Now, here's the deal. They don't give me structures. Why? That's because they think that you're clever enough to come up with the structures on your own. You should be able to use the names and draw the structures yourself. It's all about the words. Use your words. So let's look at this very first one up at the top. 3-heptine. Okay, so hept is 7. 1, 2, 3, 4, 5, 6, and 7. 3. That's the presence of the triple bond. Why is it a triple bond? Because there's a Y in E. So at carbon number 3, I see a triple bond that happens there. All right, so there's my structure, 3-heptine. Now, this is getting fancy. Acid catalyzed hydration. Hydration means water. If you hydrate yourself, what do? You drink plenty of water. Okay, well, that's what hydration means. Acid catalyzed means there's an H plus up here. We have to have that hydrogen. We have to have the acid in order for this reaction to work. So don't let the words throw you off. Use a little bit of common sense. No one said organic had to be difficult. No one said it's rocket science. Hydration means water. Acid catalyzed means speeds up using H+. Okay, now what ketones are formed? Take a look at this. Here's my triple bond. To the left, I have 3 carbons in total, and to the right, I have 4 carbons in total. This is unsymmetrical. So I am going to get a mixture of 2 different products here. So I need to be prepared to draw both, because I'm going to see both of them form. All right, so let's do the first one. 1, 2, 3, 4, 5, 6, 7. On carbon 3, there's a triple bond. So I'm going to add water. That means that one of these bonds break, it changes to a double. Two sites of attachment open up, there and there. H gets added on. Doesn't really matter, folks. Both of those carbons are identical. They don't have any hydrogens. That abbreviated structure, each carbon has 4 bonds. There's no room for hydrogen in either one of those. So hydrogen sometimes will go there. That's fine. And that means the OH will go here. Well, this is an enol. A carbon, double bond carbon to an OH. Enol. So I know that this is going to rearrange. So this double bond will turn into a single. This hydrogen will leave. My double bond basically moves. And my hydrogen goes to this side. That's all that it does, a switcheroo. Well, I don't need to write those hydrogens. I think we're at a point where we understand that they're going to be there like we do on all the other carbons. So let's just get rid of them. And there's one structure. Now, this ended up with a symmetrical ketone at this point, right? This C double bond O, look, there's 3 carbons to the left and 3 to the right. It just so happened to end up with a symmetrical ketone. But that's okay. So this is option number 1. All right, but there is another option. What is it? 1, 2, 3, 4, 5, 6, 7. Carbon 3, I see my triple bond. There we go. Just like before, my triple bond breaks. 2 sides of attachment open up. H plays with other hydrogens. Uh-oh, there ain't no hydrogens to play with. Where is it going to go? Well, up here we put it to the left. Down here we'll put it to the right. That's my other option. That forces the OH group to go here. Well, my enol has formed. Enol. So it rearranges. Double bond gets shoved up to that oxygen. That oxygen says, oh gosh, I bit off more than I could chew. I've got too much. I got to donate something. I'm going to donate the hydrogen. And there's our ketone that has formed. Where does that hydrogen go? It's got to have a home. Someone comes in and takes it in. There it is. Switcheroo. And because we're smart, we can get rid of those hydrogens, pretend like they're there, don't have to draw them, clean up that structure, and there we go. There are the 2 ketones that have formed from the acid catalyzed hydration of 3-heptine. Again, it makes you sound kind of smart when you say it that way, doesn't it? Okay, so now let's look at the ABC down below. All right, so let me get rid of these. A. Which alkyne should be used for the synthesis, oh gosh, of each of the following ketones? Oh no, synthesis means to make. These were always problematic for people. I don't know why. It just makes you think backward, though. So this is the ketone that we want to end up with, and we have to figure out, what do we use in order to get here? Well, it's no big deal. No big deal. So I'm going to draw what they give me first, CH3, carbon, CH3, double bond O. And I have to think to myself, ketone, ketone, ketone. And they want alkynes, which means that prior to this, what was it before? Well, this was a carbon single bond to an OH, and the double bond was right here. This rearranged to give me this. Okay, so I'm getting closer, but that's not an alkyne. That's an ene. That's my enol right there. So, I got to go another step further, which means I'm going to draw this again, just so you can maybe see it easier. There we go. What was this? Well, it looks like my OH has went onto this carbon, and it looks like this carbon had to have the triple bond. So if I draw the triple bond here, then I can erase that OH group. But I've also added H and OH. So I've just added OH. Where's the hydrogen? Well, this was a CH3, but now it's going to be a CH2 molecule. Again, you've got to think backward. What was there prior? So C double bond O, a ketone. That means that this was the enol that was present before this formed. If this is where the OH went, then that means the neighboring carbon probably had the hydrogen on it or added to it. So that double bond becomes my triple. I erase the OH that came from the water. And this carbon on the right-hand side, I'm going to erase that one hydrogen, to give me a CH2. And there we go. So I'm going to take this alkyne and add water and a little bit of acid to it. Think about it this way. Just double check yourself. Alkyne, I add acid and water. The triple bond breaks to a double. A side of attachment opens up here to the left and there to the right. Hydrogen plays with other hydrogens. It goes to the right-hand carbon. Bing! Right there it is. OH then comes on to the other carbon. Bing! There it is, to the left. This rearranges. An enol rearranges to a carbonyl. Boing! There it is. And that is what the question is asking. So again, we have to think backward here. Now, the question is, why did I choose to go right-handed? I didn't have to. This was a symmetrical molecule. So I could have done the double bond to the left. That would have been fine. And the triple bond would have been between carbon 1 and 2. The hydrogen here would have been a CH2. And it would have still ended up being the same thing. So no big deal if you go left-handed or right-handed with this one. It's the same on both sides. Don't stress. Don't freak out on me. Either one would be okay. Now let's look at B. Here we have another ketone, which means that this came from an alkyne. It should have. There it is. It tells me that in the directions. All right, so what does that mean? Well, I'm going to do the same thing. CH3, CH2, carbon, CH2, CH2, CH3. And then here we have the double bond O. All right, well, how do we get to that point? Well, we know that in order to get this in the alkyne world, this had to have been an OH group at one point, and this carbon had to have had the double bond. Does it go left or right? Well, we'll just pick the right-hand side for now. So there's the enol. All right, well, what does that mean? This I have to start with an alkyne, not an alkene. So this means that I've added an OH group and an H onto these carbons. So I need to erase these and draw my triple bond. All right, so I'm going to erase this hydrogen, and I'm going to erase that OH group, and I'm going to draw my triple bond right there. So there is one alkyne that I could have used in order to get to this. Now, let's think about it. This triple bond would break. Two sites of attachment would open up. OH could go left-handed. That rearranges. That gives me a double bond O. That's the third carbon in. That's where this oxygen is at, the third carbon in. Or OH could have went here. That would rearrange. That carbon double bond O would happen to the right-hand side. But folks, that's 3 carbons in from the right-hand side. And this is 3 carbons in as well. So with this particular molecule, this really is your best choice. And the reason is because no matter how this goes, you are going to see that molecule make this one if the hydrogen goes to the left or if the hydrogen goes to the right. No big deal. It's all there. But that's not the only choice. All right, so you could have CH3, CH2, C double bond O, CH2, CH2, CH3. You could have chosen this. You could have said, okay, well, there's where my double bond O is at. So this is an OH group that was here. And I'm going to erase this hydrogen. And that's where I'll draw the double bond. That's perfectly okay. Not a big deal. This is your enol. How did that enol get formed? We need that triple bond. We need this alkyne, right? That's what the directions tell me to do. Well, that means I've added acid and water, H and OH, to a triple bond. So I'm going to erase the OH. I'm going to erase the hydrogen. And I'm going to draw my triple bond between those carbons. Perfectly fine. But in this case, let's look at what happens. If this triple bond breaks, two sites of attachment open up here and here. If I put the hydrogen here and my OH here, that's great. This will rearrange to a C double bond O. That's the third carbon in, and this is the third carbon in. So this will give me the product that I'm after. Not a big deal. It works. Well, there's no difference in these two carbons. Hydrogen could go to either side. So if that triple bond breaks to a double, and let's say hydrogen goes right-handed and my OH goes left-handed, folks, this does not give me the product that I'm after. Because this will rearrange, my double bond would happen here, which is the second carbon in. This is the third carbon in. So why this works, it does. It's a partially correct answer. And that's because I'm going to get a 50-50 mix here, if this is the way that you want to think about it. Sometimes it goes left-handed. Sometimes it goes right-handed. This unsymmetrical molecule gives me the right product only part of the time. However, this option up here at the top, this is a better choice. And the reason is because when this triple bond breaks and two sites of attachment open up, if OH goes here and that's where the double bond forms, that's the third carbon in from an end. And that is what we're after. However, if OH doesn't go there, but OH goes onto the other carbon, folks, the double bond would be created there. And this is 3 carbons in from the end. And this is still 3 carbons in from the end. It doesn't matter with what direction. It's the same molecule if you gave it the name. So this is a better choice. And the reason is because no matter how this works, you're going to end up getting the same product that we're after. So this is what we're after, choice number 1. All right, now let's look at C. And let me erase this second choice just so that we've got some room to answer part C. They're trying to get me confused. They're trying to show me a ring, and they're trying to say, you can't do this with a ring, but I know that I can. I know that I can. They're not tricking me today. All right, so there we go. There's C. Do it like you did before. Guys, this is where the C double bond O is at, so I know that this was an OH at one point. I'm just going to erase that double bond. I also know that a double bond has had to have happened on either side of this thing. I've got to figure out where it goes. I'm going to do this left-handed. And that means that this CH3 is going to become a CH2. So here's the enol structure that rearranged to give me this. So how can we get this from an alkyne? Well, here's the OH group on that carbon. I have a hydrogen to the left. So there's my H and OH. So I've added water. All right, so just like before, what we've done, I'll erase this OH. I'll erase one of these hydrogens, and I'll draw an extra bond there. And there's your alkyne. So when this alkyne breaks, a state of attachment happens here and here. Hydrogen plays with other hydrogens. It's forced to go there. And my OH will go at this position. This rearranges, right? The C double bond O will form at that spot. And that is what we're after for my product. All right, so there's the alkyne that we need to use. Now, let's question, why not the other way, right? Okay, well, here is my double bond O. Let's start back from square one. And here is my CH3. So I chose to go left-handed. Why didn't I do right-handed? Well, let's see. All right? That's no harm in asking. It's part of what this class is about. So if this is where my double bond O was, I know that at a certain point this was an OH, and let's say my double bond is going to be here. All right, well, here this carbon is perfectly fine in the ring. It's got 1, 2, 3, 4 bonds at this point. All right, so there's my enol, and this enol will rearrange, and it will give me this. But the question said which alkyne should be used. All right, so what that means is that I go through, I erase the OH, and then on the other carbon that's involved in this bond, I need to erase a hydrogen. But this carbon has 4 bonds. There's no hydrogen here anymore. I don't have an extra hydrogen to take away, which means that I cannot put a triple bond here because look at what happens if I do. This carbon now has 5. We can't have 5 bonds. 1, 2, 3, 4, 5. This is not allowed. That carbon is way bit off more than he can chew. Sorry, can't work. So that is why this is not a possible choice. There is no hydrogen for me to erase in order to create this triple bond. Because of that, that triple bond could not have happened on that side. And the only choice that I have here for an alkyne is this one. That's it. Triple bond breaks to a double, H goes to the left, OH goes to the center. That OH rearranges to a double bond O. That is the only route that will work in order for me to get part C. All right, so that's where this video is going to stop. And the next one we'll pick up from here because there was more than one way to add acid and water, right, to get an OH group onto a molecule. So we're going to look at these other possibilities, and we're going to see what happens here. Stay tuned.